Hi, everyone. Welcome to our senior design presentation. Our group was focused on the wireless audio transmission of audio signals using laser pointers. And I'm Cole Foster.
Hi, my name is James Haddock.
My name is Siobhan Patel.
I'm Jared Schwartz.
My name is Gina Mendoza.
And our faculty mentor is Dr. Ameta Kosman.
So why are we doing this? Secure communication is vital to protect data and national security. The aim of this project is to create a secure means of communication, avoiding hacking attempts and eavesdropping. We would like to use affordable components to transmit the signals while making sure that we are maintaining its integrity. To ensure secure transfer of the signal, we will add security measures that will be shown and explained later in these slides. To achieve these goals, here's a system that we have developed consisting of two subsystems, which are shown on the next slide.
Here we have our final design circuit. Starting from the left, the aux cord takes in the audio signal. It is then modulated and sent to the laser pointer. On the receiving side, the solar panel takes in our signal. It is then demodulated, filtered, and then amplified to be clear and understandable for our speaker to play out. We wanted our system to be secure, so we chose modulation as our form of encryption. There are four types of modulation that we looked at. Frequency modulation, which changes the frequency of the signal to compress or expand depending on the carrier wave used. Pulse width modulation, which changes the signal by chopping it into different parts. And lastly, phase modulation, which changes the signal's amplitude while retaining the peak amplitude frequency. The fourth option was amplitude modulation, which is the one we chose. From the graphs, we can see the signal amplitude changes after it is multiplied with carrier wave. Graphs 1 and 2 are multiplied together to get graph 3. This in turn encrypts our signal using low-cost materials. Once the signal is modulated, it is then sent to the laser.
Since a solar panel is to be used as the photosensor for the receiving subsystem, it is important to figure out which laser will the solar panel respond the best to. The three lasers we ordered had a wavelength of 480 nanometers, 547 nanometers, and 623 nanometers. Each laser was connected to a power supply, then shined onto the solar panel, which was connected to an oscilloscope. The oscilloscope measured the voltage response of each of the lasers respectively. This collected data is summarized in Table 1, where you can see each of the lasers shown here. We can also see the minimum voltage each laser required as well as its associated minimum current. The minimum current and voltage were both calculated using a power supply. The electrical current was then determined and the voltage response was found using the data obtained from the oscilloscope. The data was analyzed and it was found that the 547 nanometer laser consumed the least amount of electrical power and it also had the best voltage response when shined onto the solar panel. Based on this data, we can confirm that the 547 nanometer laser should be our best choice when we use a solar panel as a photosensor.
So to get the signal from the laser pointers, we needed some sort of photo receiver. And we ended up moving forward with the solar panel. This was the best option because of essentially its large area, which is easier for user interaction. And some of the other options were extremely small, like the resistors or the diodes. So this was really the best option for that. Additionally, the solar panel was low cost. It was about $8 on Amazon, which is very reasonable for our project. We knew that the solar panel would invite some problems with it. More noise would be added to the system from ambient light, which would have to be filtered out. And we also found some other issues when we looked at the frequency analysis. So we looked at the quality of the signal preservation throughout its transmission. The three graphs on the bottom, the left one would be the 10 kilohertz sinusoidal signal that we chose coming out of the waveform generator. So that spike in the middle of the graph is that 10 kilohertz signal. The middle graph shows the introduction of this big sinusoidal pattern, and that was from the DC biasing. So we had to up the voltage to power the laser, and it introduced that noise into the system. And you can still see the 10 kilohertz signal there. However, in the last graph is the signal after it's collected by the solar panel. And you can't see that 10 kilohertz signal there, which was the important information. You still have that sinusoidal, and you can see that it was kind of smoothed over, which suggests the capacitance of the solar panel. But this really this analysis of all this shows that there's a lot of improvement to be made in the area of signal preservation within our transmission system.
After the signal is received from a solar panel, it needs to be demodulated so that it can be understandable. To demodulate a signal, we take our modulated signal and multiply it with the same carrier wave used in the modulation. This takes graph 1, multiplies with graph 2, and produces graph 3. This demodulation process returns the signal back to a form we can understand. However, the signal will not be as clear as we would like it because of the noise picked up during the transfer process. Thus, our signal would need to be filtered and then amplified.
Initially, when choosing a filter for the receiving subsystem, we had multiple options which included high pass, low pass, band pass, and band stop filters. Ultimately, we chose high pass filter, and through experiments done throughout the year, we decided on a third order high pass filter. Due to the current events, we were not able to physically create this filter. However, we were able to design and simulate it in LT Spice to get a fairly accurate idea of how it works. We chose to have a 500 Hz cutoff frequency to be more precise on which frequencies to let pass. Using the simulation, we were able to produce a Bodie plot, which is shown right here. This plot approaches 0, which corresponds to a gain of 1. We also checked the Bodie plot at -3 decibels because that is approximately where half power is. We were also able to generate a transfer function to be able to relate the input with the output. This was done by calculating the equivalent impedance and applying voltage division on this circuit. Using this third order filter, the overall impedance is lower, so our signal will naturally be louder than if it was when we tested a first or second order filter. However, depending on what output device is being used, we would amplify accordingly.
When considering amplification, there's a ton of different circuits we could have used, but using an op-amp was the most straightforward and cost-effective option. The op-amp chosen was designed for small signals like audio signals, and aims to add as minimum noise in the process as possible. Looking at figure 12, you can see the circuit diagram for the amplifier. Through circuit analysis, we can find the transfer function. Looking at the transfer function at the top, you can see that it'll just be a constant number depending on the values of the resistors in the circuit. Using MATLAB, we can look at what the frequency response of the filter, amplifier, and both systems in series would look like. As you can see, when we have both systems in series, we are able to block low frequencies and provide gain at high frequencies. For the rest of the semester, I began simulating the project as much as I could to make more progress. Looking at the circuit diagram in the bottom, you can see the audio signal coming in and it is being modulated. I was not able to make the modulating and demodulating circuits because the program does not have the components. However, I was able to simulate it by multiplying the audio signal with a high frequency carrier signal. The green wave is the audio signal by itself and the blue wave is the modulated signal. They don't look too different. However, when we zoom in, you can see that they are, and we do have that change in shape that James showed us on his slides. However, I also wanted to play what both of these audio signals sounded like. So here's the input. And here's the modulated signal. As you can see, that just by multiplying the signal with another high frequency signal drastically changes the shape and sound of it. So this is the simulation for the receiving system. If you look at the circuit diagram in this first circuit, I am just simulating what the solar panel would have done, which would be to add 60 Hertz noise. Next, I am filtering it and then amplifying it. Now, I've tried this with a modulated signal and tried to demodulate it in the process, and it doesn't really work. So I don't know if that is because of LT Spice or because of the noise being added, it can't demodulate properly. However, this may be an issue that we would have ran into in the lab, and maybe amplitude modulation is not the best method. However, looking at these results, you can see the first wave is the input, The next is the solar panel, filter, and amplifier. And I will now play all these audio files for you, except for the input because it's the same song as the last slide. Here is the solar panel. Here is the filter. And here is the amplifier.
In conclusion, our system as a whole is able to transmit audio signals wirelessly and remove unwanted noises. For our application, solar panels did work, however, they may not be the best option. Although we were not able to physically complete this project, the use of simulation programs allowed us to see what our outcome would have been. Some of these results include that amplitude modulation would work as an encryption method, however, for us it did not. And the use of amplification was able to strengthen our signal. Are there any questions?